All right, in the last video what we did was we talked about resistors in series, and that was a particular kind of situation where the resistors followed one right after the other. In this video what we're going to do is we're going to talk about another simple circuit where the resistors are next to each other in the sense that they branch off from a single point and then connect back up to a single point. The way that we think about this is in terms of the fact that these two resistors are parallel to each other in a sort of schematic sense. And so what we do is we refer to this as resistors in parallel. And this is going to be a little bit different than the situation that we had before, but we can still apply the same principles of charge conservation and energy conservation to them to understand it. So what's different about this is that when we apply this idea of charge conservation, which suggests to us that whatever current goes in has to be equal to the current out, we have to actually look at a specific branching point, that is where the current might separate or distribute in some way. So that occurs right here at that branching point. And so if we were to blow that picture up a little bit, what we would have is a situation where we have the total current that goes through the battery coming through, and it branches off into the current that goes through resistor 1 and the current that goes through resistor 2. And so whereas before we had the current that goes through the first one is equal to the second one is equal to the battery current, in this situation, because of this conservation of charge, the current that goes through the battery must be equal to the sum of the currents that branch off. Now this is a slightly different scenario than we had before. It's a slightly more complicated, but it still uses that same fundamental principle. Now, additionally, we can use this energy conservation idea, the idea of energy conservation per unit charge, adding up the energy that's used around the loop. But now the situation, again, is just slightly more complicated. There are at least two loops in this picture. The first loop you can think of as going through that first resistor. So that would be loop 1. The second one you can think about going through just, the second resistor. That'd be loop 2, right? And in both of those scenarios, when we go around those loops, because they're fully closed loops that start at the battery and end at the battery, all the energy that's available gets used in those resistors as you go back around. Now, an additional way to think about that is that all of these pieces of material are metallic, meaning that the potential difference across these two resistors is exactly the same, because the potential at this location and the potential at that location are going to be the same. So whatever sort of available energy we have to use across these things is going to be exactly the same. Now that doesn't mean that they drive the same current, because the resistors are going to be different. So what we'll do is we'll add up all the energy around the first loop. So loop 1, and note that it's going to be equal to 0. So in that case we'll have the energy associated with the battery, which is the source, plus the energy associated with the first resistor, right? And similarly, if we think about the potential difference across loop 2, it's going to be equal to 0. Again, the source is the battery, and the sink, or the user, is the second resistor. And just as before, the battery being the source and the resistors being the users, when we apply Ohm's law to them, we're going to introduce a minus sign to indicate that they are using up that energy. So what we'll have is that the battery potential difference is equal to the current through the first resistor times its resistance, and it is also equal to the current through the second resistor times its resistance. So it's equal to both those things, and you can see that depending on the particulars of the resistors themselves, those currents could be different, right? It could be higher or lower, but they still use the same, they still have the same potential difference across them. So now what we're going to do is we're going to play that same game that we played a moment ago, which is, can we get the same effect, namely the total amount of current through the battery, to be the same if we were to replace these with one resistor? So in this scenario, what we're doing is we're taking this set of parallel resistors, replacing it with an equivalent resistance, and asking the question, how much what is the equivalent resistance that we need to drive the same current that would be coming through the top of this branch and the bottom of this branch. Now we can't say anything about what's going on in here, but we can say something about what's going on in the rest of the circuit. And this is that idea of equivalent resistance. So what we end up doing is we end up saying something about how these two are related to each other, namely that the delta V of the battery over the equivalent resistance must be equal to the total current that we see, which was equal to I1 plus I2. And those two things are exactly equal to delta V of the battery divided by R1 and delta V of the battery divided by R2. Now all of these equations share the same delta V battery in the numerator, so that means that our relationship between the equivalent resistance and the individual resistors is this kind of strange looking sum where first we say we can describe 1 over the equivalent resistance as the sum of 1 over each of the resistors in this parallel situation. And that actually abstracts out. We can continue to add more resistors if we were to add more of them in parallel. So this relationship is slightly more complicated than we had before. However, what we're going to find is that this is in a sense related to the available area that the resistors have, and you have now a larger area through which the current can pass, and therefore you would expect a greater current when you start to put them in parallel like this, as opposed to a longer resistor which would have more resistance when you put them in series. So this is still connected to sort of those microscopic ideas, but we're really focusing on the macroscopic engineering design. So all we've done here is apply those principles of conservation of energy and conservation of charge to a set of parallel resistors to derive what the equivalent resistance would be to drive the same current through the battery as we would have in this scenario.